Good afternoon, everyone. Welcome to this webinar. We are very happy to have Professor Nana Liu with us today. Nana and I met long ago at various conferences, and we met recently at Aquis in Seoul, where she gave a very nice talk. And it was so nice that we thought we need to invite her to give us a special edition just for us. Yeah? So Nana did her PhD in Oxford, where she was a Clarendon scholar. Then she went for a postdoc position to Singapore at the Center for Quantum Technologies, and then later the Singapore University of Technology. Later on, I'm not sure. No, but I think
you
now
don't have to read the whole thing.
Yeah, no. Now you are based in Shanghai as an associate professor for quantum information and technology group. Yeah, so thank you very much, Nana, for being with us today. I know that it's a late Friday evening where you probably have better things to do.
I'm very happy to be here.
We really appreciate the fact that you are happy to give us the talk. So you're most welcome to share your screen and start your presentation. Thank you very much.
Yeah, sure. Okay, we have one newcomer. I didn't get the name.
Amy, yeah.
Oh, hi, Amy.
Hi.
So Francesco, since it's like a fairly small group, so like I would
a few of us are online. They're probably
sorry, I didn't see
couldn't be here in the room. Yeah.
Okay, but it's still like given a fairly small like intimate group, I would say, you know, it would be nicer to have this more of a discussion, like more of an open discussion. So please feel free, like instead of a lecture format. So please at any point, like just interrupt and please like unmute. Or, oh no, you don't need to unmute. Like, or for those online, you can unmute. I get used to it because when I teach online, I always say this. But just shout out. And then we can have a discussion and focus on anything particular that you guys are interested in, because most of you guys are in Francesco's group, so you guys would have particular interests. Yeah, so just feel free, like just interrupt me at any point. Okay, so let me share this. Now, can you guys? Oh, let me see if I do share slideshow play from start. Can you guys all see this?
Yes.
Yeah.
Okay.
All right, so thanks everyone for coming. I wish I was there in person. Francesco told me, how wonderful Stellenbosch is. I hope to visit at some point. I'm based in Shanghai at the moment, and for the last year or two, I've been concentrating on quantum algorithms for scientific computing. Okay, because you would have heard a lot about different applications, and one of the most important applications of scientific computing is that of partial differential equations. And I think you guys know that, I'm assuming most of you guys are physicists. Is that correct? Yeah?
Yes.
Okay,
almost.
yes.
Some computer scientists, one at least. Some computer scientists.
Okay. Well, so then you will know that, the study of physics is basically the study of partial differential equations, right? So all the laws that we know about, they're put in this kind of form. And, and our question is, with partial differential equations, we know that they can often be very difficult to solve. One question of difficult to solve is analytically, but another is actually how to solve them even numerically. And, especially when we start having very high dimensional partial differential equations or PDEs, they become sometimes intractable. Okay, and especially nonlinear type of problems, it's still a big problem, not just for mathematicians, but of course for industry. And in the quantum world, we're doing quantum physics. Then our question is, well, what about quantum simulation, right? So, and we know that quantum simulation was proposed mostly for simulating one particular PDE, and that is Schrodinger's equation. And now our question today is, is it possible to also directly simulate, in the simplest way as possible, other types of PDEs? Okay, and in particular, so I'll just explain the title a little bit. So you guys know the word quantum simulation, and you know the words partial differential equation, but what about the word analog and Schrodingerization? Well, Schrodingerization is the method that I'll introduce to you guys today. it's a very simple way of transforming partial differential equations which are not of Schrodinger's form, right? And it's a procedure for putting them into Schrodinger's form, so then you can use quantum simulation. And the word analog here is refers to continuous degrees of freedom as opposed to discrete degrees of freedom. Okay, so I'll explain this as we go along. Okay, and remember, guys, if you have any other questions along the way, like please interrupt and we can discuss it. So this is more of a discussion. Okay, so when we think about quantum simulation, like usually you guys are probably thinking about two kinds of things. Okay, so one is that you may be thinking about simulation of the system of ordinary differential equations of Schrodinger's form. Okay, so on the left-hand side. And there you may be looking at, log capital D two-level systems. So this was the original way that Feynman would propose this. And in this case here, you're describing your fundamental degrees of freedom in terms of discrete variable qubits. So these are your two-level systems. And then your Hamiltonian, okay, H, is then a D by D Hermitian matrix, okay, but it's finite dimensional matrix. And then if it's already in this Schrodinger form, then we know the solution, okay, to the system of ODs is of the form that, you prepare initial state and then you apply unitary operation. That's of the form e to the power of minus IHT. Okay. Now on the right-hand side is another way of thinking about quantum simulation. And this is what I mean by analog in the continuous form, whereas in the previous ones, the discrete variable qubit form. On the right-hand side is really think about Schrodinger form in the full, PDE formalism. And this is the equation you guys are all very familiar with. Now, the Hamiltonian, on the other hand, when we express it in terms of our momentum and position operators, this is no longer, finite dimensional matrix. I mean, if it's in a matrix representation, this is an infinite dimensional matrix. Okay, but this is an operator now acting on an infinite dimensional Hilbert space, no longer, no longer a capital D dimensional Hilbert space. But then if you want to solve for your final state, again, you apply unitary, okay, that's e to the power of minus IHT, but now your H with a subscript CB for continuous variable, it's a continuous operator, okay? And what it's operating on are not, a system of qubits, but of Q modes, all right? So do you guys all know what I mean by when I say Q modes? So qubits refers to like quantum bits, okay? Q modes refers to quantum modes. So now U in this case is essentially the wave function. Okay, it's just a fancy word. Okay, that but it's something more familiar to physicists than qubits actually. All right, so far so good. Okay.
Thank you.
Now, just a reminder, okay, what I mean by ODs and PDEs, okay, with multiple initial conditions. So on the left-hand side, when we say we have a system of capital D ODs, we want to solve for this X, okay, but now this X varies with respect to one parameter, okay, which we can call time, for example. If we have a system of multiple initial conditions, it means that X, you might have multiple initial conditions, but the OD itself, okay, it remains constant. And now this function f, if it's linear function of x, then it's a linear OD, but otherwise it's called nonlinear, okay? And on the right-hand side, we have the PD formalism, okay? And the difference between OD and PD is now that the PD, you have variation not just with respect to time, but other variables. So if it's D plus one dimensional PD, then it also depends on D other, okay? Usually like spatial dimensions. And in this case, you can also have, M initial conditions that obey the same dynamical equation. And it's important to think that actually PD is, you can think about a PD really as an infinite number, okay, of ODEs, okay, because you can always discretize your spatial derivatives on the PDE side, and then you write them as a system, okay, of ODEs. Okay, so, and sometimes what people do is that, in principle, a PD is really an infinite number of ODs, but what some people do is that they truncate, okay? So you write that out as a finite, but very, very large system of ODs. And that's what people sometimes use for numerical simulation purposes. Okay, but what we like to do today is that we're utilizing quantum, okay, simulation, so we don't have to do that. Okay, so we keep the full structure of the PDE. Oh yeah, and f here, okay, on the right-hand side, again, if f here is a nonlinear function, then we call that a nonlinear PDE, which is, notoriously difficult. But if it's linear, then, it's a linear PDE. Okay. All right, so, and just a word on classical versus quantum solutions. I know most of you guys know this already, but I do want to emphasize this because it's often not emphasized. That, when we talk about, solving, and, a lot of papers, they write solving, but really what they're doing is they're simulating, okay, the solution in the form of a quantum state. So the classical solution, the output of a classical computer outputs x, okay, or u, okay, and they can output x and u for all values, okay, of the arguments in time or space. But the quantum solutions, typically what they do, because it's on a quantum simulator or a quantum computer, the output of that is really a quantum state, okay, before you make measurements. And typically what you have is a quantum state whose amplitudes are proportional to the solutions that you want. Okay, and you can also, and I'll describe ways in which you can have other embeddings, like for certain benefits. But it's important to note that the only way to really compare them one to one is to have an observable at the end. Okay, so for the because in most cases of PDEs, we may not care about the actual solution at every single point, but we do care about ensemble observables. Okay, and in that case, it may be possible for quantum to have an advantage, because if we want to extract classical values of the amplitudes from the quantum state, we would lose any advantage we could have, okay, at the beginning. All right, so now when we, if our question is, well, how do we use quantum simulation, okay, for other PDEs, well, there are two questions to ask. First of all, how do we actually embed the information of the ODE or PDE into the quantum system? And we have to make a choice. Okay, do we have to do it through qubits, so discrete variable, or do we embed it through the continuous variable of these analog systems, or maybe some hybrid? Okay, so that's one choice we have to make. And the second one is then, how do we actually turn the non-Schrodinger's equation into Schrodinger's equation? Okay, and we really want the simplest form possible. Okay, and I'll describe some benefits of the continuous variable analog formulation first. Now, the Schrodingerization formalism I'll introduce, it actually works for all, CV, DV, or hybrid, but I think it's much more natural, okay, for us to concentrate first on the analog formulation. And one benefit is that in this case, there's no need to discretize the PDE. So like I was saying before, like, a PDE is really an infinite number, okay, of ODEs, and what people do is that they discretize and then make it into a finite system, a very large finite system ODEs. And in that case, what you're doing is that you're discretizing a derivative. Because when you think about fundamentally what a derivative is, it's a limit when you take rise over run. Okay, so it's like a gradient. And you only approximate the true, gradient if you take the increment size, okay, to be very, very small. And you can imagine now the precision, okay, to which you, characterize the derivative to depend on how, small you take those increments to be. But if we actually have a continuous variable formulation, there is a way actually not to perform any of this discretization at all, okay? And I'll show you how that works. And the second benefit is that then we can potentially utilize existing Hamiltonians, okay, without breaking them up into a lot of gates. Okay, so this is like the case in analog quantum simulation, because if we do everything using qubits, we actually have to break them up into lots of gates, because there are really no natural Hamiltonians actually to perform that evolves in the way that we want. Okay, and thirdly, I like to make a comment on like how I view the development of quantum computing, because I look back into history and you think about, well, how did the history of classical computing evolve? Well, there was a very long time, okay, before the dominance of digital classical computing, which was really only became fully dominant in the 1980s, and that was a period where before digital computing was dominant, and that was because error correction for digital computing, for classical digital computing, was not as good. Okay, and during that period of time, analog classical computing dominated. Okay, and there were lots of different types. But whereas in the quantum computing community now, it's as if we're we don't have a lot of analog computing. Okay, so today classical analog computing is also making a comeback classically, right? Because as we're going beyond the Von-Neumann architecture, people are looking for all kinds of ways in which we can use physical systems to mimic computation or other physical systems. And especially if we're solving PDEs, and of course, PDEs is giving us, one kind of physics, like a particular PDE is telling us one kind of physics. We're using another, physical system to mimic another. Okay. And lastly, it will become clearer when I talk about this, like I'll show you more explicitly later on, but the CV formalism touches upon more foundational questions directly, okay, about how one physical system can emulate another. Okay, and we can see the resources a bit more clearly. All right. And this is just, a little table there just to make a little bit clearer, okay, what I mean. Because we really have 4 types of computation that we might have in mind, actually. And sometimes it's clear just to have this so we know, if we're comparing oranges to apples or not. So of course we have classical and quantum, but we also have analog versus digital. And analog without the UE at the end, I refer to as like the computers based on continuous degrees of freedoms. Okay, so for classical, of course, we have digital classical, okay? And for PDEs, in that case, they often suffer from the curse of dimensionality, which means that the cost for like solving the PDE, it becomes exponential in the dimension. Okay, so that's the curse of dimensionality. And for in the classical world, people also have analog devices, but for PDEs, they don't have analog devices for PDEs directly, but what they do have are analog devices for ODE systems. And then what they do, they discretize the PDE and they parallelize. Okay, so they get a lot of these analog devices, a very large system analog devices to solve for lots of ODEs. But here again, you're not really solving for the full PDE. And in the quantum case, most of the algorithms that, people talk about where they prove, advantages with respect to whether or not you believe them, they fall under digital quantum. Okay, so, and in this case, again, you have to discretize the PDE, and these are mapped onto qubit dynamics. And remember, in our very first slide, we had the left-hand side and right-hand side, okay, or quantum simulation, and this really belongs to the left-hand side, okay. And finally, we have the quantum analog, okay, so, and this is what I'll introduce today, where our PDEs map directly onto the continuous quantum system, okay, and here we, where we can also, resolve the curse of dimensionality, although I would say it's really also comparing apples to oranges, because as you can see from, this table, that they don't really belong, to the same, either the same column or the same row. Okay, so, and yeah, so then I think in this case, it's not so meaningful to directly compare, okay, but still like kind of a rough comparison. Okay. All right, so now the main thing, okay, how do we actually turn Schrodinger's equation into a non-Schrodinger's equation into Schrodinger's equation? So this is part A. Now, we have qubit formulation, okay, so, and we also have the CV formulation, but I'll focus on the CV formulation today. Okay, so now if we think about linear PDEs, okay, so we're going to concentrate on linear PDEs first, and we have an example, okay, du dt is equal to some linear operator applied to u. Okay, and we have Schrodinger's equation, and then we have the heat equation with a forcing term. Okay, so if you notice, they're basically the same. Okay, and the only difference between them you see is a little I there that is different, and you're like, oh, so close. Okay, so so close but no bananas, right? So then you say, well, how do we actually turn the heat equation into a Schrodinger's equation? Okay, so you say, well, it's just an I, right? So, and a lot of people notice that, yeah, it's just an I. Okay, so then what you do, and this is the warm-up heat equation example. Okay, so one popular method that people use is called imaginary time evolution, or in some contexts, it's called the Wick rotation. And there you just go from T to IT. Okay, because it's just an I. Okay. However, and this is, and people write all kinds of papers on this, okay, and they also have, NISC versions of this as well, okay. However, one important thing to note is that imaginary time evolution solution in T, it does not give the solution to the heat equation in time T. Okay, so the only time when, they would agree is in the asymptotic limit, okay, when T goes to infinity. Okay, so, but of course, when we're solving for PDEs, we actually care about all the other T's, okay, all the other time that goes in between. So we really want a real-time way to Schrödingerize the heat equation. And one way that the imaginary time evolution community gets around this problem is actually they would perform. You need to perform partial tomography at every step, okay, to actually even know, okay, which Hamiltonian to perform at the next stage. So it's not even clear, okay, how to do that without disturbing the system, okay, quite significantly. Okay, so now is there a real-time way, okay, to Schrodinger the heat equation? And this is what we call Schrödingerization. Okay, so first I want to introduce a quantity called W. Okay, so we want to solve for this thing called U. Okay, U that depends on T and X. But let's introduce one extra spatial dimension, which I'm going to call psi. Okay, and then we're going to multiply this U by this amplitude e to the power of minus psi. And I call this the warped phase transformation because we're introducing this extra parameter, okay, psi, which you can think about kind of like in phase space. And it's warped because in the extra dimension, there's this exponential fall off. Okay, it's inspired by a high energy physics model, which I used to do. So that's why it's called warped. Now, so now you say, well, what's the point of that? Well, because remember, I'm not going to read, line by line first, but I'll just give you the intuition, so you can believe why this damping should work. Because remember, all we want to get out is this extra I, okay, from somewhere. Okay, so how do we get this extra I back? So if we look at W on the bottom, right, if we see Fourier transform in psi, then the Fourier transform of W is W tilde. Okay, and if we look at the definition of the Fourier transform, what you do is that you multiply, okay, W by e to the minus I psi eta. Okay, and then you take, then you integrate over the extra dimension. Now, if we want to, and of course, to get W, from W tilde, then it's like the same thing, except now it's e to the power plus I, okay? Or psi eta, where eta is the Fourier mode, okay, to psi. Now, how do you get an extra I there? Well, then you notice to get an extra I, you just take a derivative, okay, with respect to the extra dimension. Okay, so that's how you get an extra I. So now if we look at the heat equation in phase space, okay, then we see this W, okay, can be dependent on the first derivative, okay, of this W. Now, but of course, we actually want U to solve the heat equation. Okay, so we want the dW d psi to actually reproduce for us W, okay, or minus W. And how do we do that? Well, the only way to do that is to multiply, okay, e by e to the power of minus psi, because if you take the first derivative with respect to that, you just get minus W back. Okay, so hopefully this gives you an idea of, or motivating why we take this transformation. So now if you go through all of this, then you see that W tilde, okay, so satisfies a PDE in the equation in blue, okay, in the second blue box. And what is that? Okay, we get our extra I there. Okay, and that's really a system of Schrödinger's equations now, okay? And it's that in real time, okay? Because now this t goes to eta t, but eta, remember, is the Fourier mode to psi. So this is like the range is that of the real numbers, okay? And now we say, well, how do we now realize this on a quantum system? Okay, now this is now of the form that we want, okay? A system of Schrödinger's equations. Yeah, so in this case, okay, so we want to solve for W tilde first. Okay, we'll talk about how we get U back later. Now, because now this is a system of Schrödinger's equation, well, we want this eta, the Laplacian, and the V to become operators. Okay, so we can get our Hamiltonian. So what are these operators? Well, we know that x goes to x hat. Okay, right? And now the derivative, okay, d dx, well, we know from our first lessons in quantum mechanics that we can associate this with minus IP hat, okay? So like whenever you see the Laplacian is just like taking second derivatives, okay? So you can replace that by minus, p hat squared. And then v of x becomes v of, x hat. Now we have this extra eta. So now remember this extra eta is acting on this new degree of freedom. So this, extra mode that we have, right? So now our Hamiltonian, h of CV, is the part where we have the Laplacian and the potential. Now it's a cross product, right, with eta hat. Okay, but eta hat is just a quadrature. So it can be, x or p, and we just choose, eta to be x for simplicity here. Okay, so which means that now if we have access to this Hamiltonian, okay, which has the form minus p squared plus v x hat times a product with x hat, And then we do e to the power minus iht, okay, applied to the initial state, then we can actually get w tilde in the end. Okay, and then how do we recover u? If we go back to the second line, we can actually recover u by actually taking an integral, okay, of w. Okay, and I'll show you how to do that in the quantum way, but you can see how we can recover, okay, our u. So now the general methodology to do this, again, it's very simple, okay? So I mean, there are a lot of symbols on the slide, but it's actually very simple. That with any of the PDE that, you know, its first derivative in t, and d spatial dimensions and kth order derivative, whenever you see x, okay, change it to x hat, okay? Whenever you see a derivative, okay, with respect to x, you change it to minus ip hat. That's it. Okay, so, and remember, if we have d dimensions, then it's with respect to x subscript j, and j goes from 1 to capital D, right? So then your momentum mode should be acting on the corresponding jth mode, okay? And if it's to the kth derivative, it's just minus ip hat to the power of that k, okay? And if you do that, then you end up with an operator, okay, a here, okay? And a generally, okay, is neither Hermitian nor anti-Hermitian. Okay, so if A is Hermitian, then it means that you already was in a Schrodinger form. Okay, so you don't need to do this. If it's anti-Hermitian, that's just like the heat equation case we looked at. Okay, but in general, it's some combination in between. Okay, but that's very easy to solve because A can always, you know, very simply be written as a sum of a completely Hermitian part and a completely anti-Hermitian part. Okay, so the Hermitian part is just a sum, you know, a plus a dagger, okay, and the anti-Hermitian part is just I, a minus a dagger. Okay, so it's so once you have a, it's very easy to decompose this. So then the corresponding Hamiltonian, okay, for this system, for this more general system is if we look in the blue white box at the bottom, we have the form of H, and this is equal to A2, okay, tensor product with eta hat, okay, plus A1 tensor product with the identity. Okay, and this is quite you know, simple to motivate, you know, why you should have this form. Because remember, if your A is already Hermitian, then it's already in Schrodinger's form. Okay, so that means you tensor product with the identity because you actually didn't need this extra mode. Okay, and then remember for A2, that's a completely anti-Hermitian part. So that was the heat equation example that we had to look at. And remember what we had to do was we had to tensor product with eta hat. Okay, so that explains now why the total Hamiltonian is A2 tensor product eta hat, okay, plus A1 times the identity. Okay, and then we can have, you can write down the corresponding initial states as well, but I put it in the quantum circuit, so it'll be easier to see later. Okay, so do you mind? I'm just going to turn my aircon on. It's just getting a little warmer in this room now. Okay, I'll be right back. And if any of you guys have any questions or anything, just like please interrupt me at any point, and we can chat about it. Okay, so so in terms of a like a circuit diagram that we can have, what you need to do is that we need to prepare initial state that whose amplitudes correspond to the initial state of our PDE, the one that we want to solve for. Okay, so that's U of 0 on the bottom, and then we have an ancillary state that we need to prepare. Right, and then he has this form e to the minus psi, okay, and this is what we saw before. This is like part of the warp phase transformation. And when you look at this state, you're like, oh, okay, I mean, this is not quite a Gaussian state, okay, but it's very, very close to one, right? So, I mean, of course, this is a state that, you know, I've spoken to many experimentalists, and some, they're like, oh, yeah, like they can try and, you know, approximate this state. But for once, for people who, you know, don't have control, experimentalists who don't have control over the initial state so much, most often they do have access to what are called Gaussian states. Okay, so this, if you look in the little orange box or peach box down there, then you see G. Okay, the G state like that is a general form of a Gaussian state, and this, especially in photonic systems, this is quite this is very accessible. Okay, and in particular, we have this parameter called S. I mean, this tells you how fat, okay, the Gaussian is. And it's order unity, so it's basically like the output of your laser, okay, that people have, right? So, and we see that it's actually very, very close to, you know, just a laser or coherent state, because of fidelity is like 0.986. Okay, so even if you don't have access to once we can approximate the true ancilla state that we want, we can still get pretty close, okay, experimentally. Okay, so now we prepared the initial states, and then they have an interaction, okay, of the form with the Hamiltonian that I was saying before. So that's A2 cross eta hat, and A2, remember, is the completely anti-Hermitian part, okay, of your A, and A1 is the completely, Hermitian part, okay, of your A. And then, so we have the output at the state. Now, if we want to have the output of U of t, okay, so output state, then we need to measure the ancilla state, okay. So, and the measurement, like, we don't need precise momentum measurements, okay, like in any particular measurement, which can have high errors. But instead, what we have is something like a parity measurement, okay, so where we only need to pick positive momenta. Okay, so and once we have that, then the bottom state, okay, it's the state that we want. And yeah, okay, so and then but because this is probabilistic, okay, so then we actually get positive momenta, okay, with the probability that's proportional to the ratio, okay, of the norms, okay, so of U of t divided by U of 0. So if it's a conservative PDE, so a conservative PDE is when your norm is preserved, like Schrodinger's equation, for example. But the heat equation is the exact opposite of that. Okay, so so in that case, it's not preserved. Okay, so then this probability will then depend, okay, on how conservative or how dissipative, okay, your PDE is. But if you look at the size, okay, of this system, then we only need one ancilla mode. Okay, so if we have a d-dimensional PDE, then in total we only need d plus 1 modes. Okay, so it's not exponential. And if we think about like the gates that we need, well, this is when it really depends on your PDE, and I'll explain. You'll see lots of examples later, because because everything here is continuous variable, and we know that quantum systems, they're really continuous to begin with. Okay, most of the time. Then it can be the case that there are some Hamiltonians which are naturally occurring that would fit this form. Okay, or we can break this form up into not too many continuous variable gates that we can start to realize. Okay, so therefore what we would consider as kind of a natural gate count that could vary depending on the PDE. All right, and here we can also extend. So I showed the example for inhomogeneous PDEs and first time order derivatives, but of course we can also extend this to inhomogeneous PDEs and high order time derivatives, okay, as well. So this is the summary chart, okay, on what to do. Okay, so if you want to simulate a linear PDE, okay, of the form in blue, then what you do is that whenever you see x, you put x hat in. Okay, whenever you see a derivative, okay, you put minus IP hat in, and then you end up with an operator, okay, of the form of A. And you separate, this operator into its Hermitian, okay, and anti-Hermitian parts. And the corresponding Hamiltonian you want is then the anti-Hermitian part, okay, cross eta hat, plus the Hermitian part cross the identity. Okay, and that's it. Now, we also have a qubit version of that. So it's actually very simple to, discretize, okay, what we have. And have a qubit version. And the benefit of the qubit version, at least for computer science people, is that then we can give them a more, a query and a gate complexity, okay, for this, okay. And you can also apply this to things like, ground state preparation or Gibbs state preparation. But I won't speak so much about this today, but you can ask questions about that as well if you like. Okay. All right, so now you may ask, where is the quantum, okay, in all of this? Right, so if we have qubit-based algorithms, you could say, oh, we need these T gates, or we need entanglement with these C naughts, and therefore we think that it's not classically simulable. All right, so but how do we see it here? Like, where are the quantum resources that we're using? And an important foundational question is, which PDEs are classically efficiently simulable and which ones are not? Now, in the qubit language, it's extremely hard to see, okay, for the PDE question, where the real quantum part comes in. Okay, so there is a Gottesman-Nil theorem, okay, which says that only Clifford gates and projective measurements in the computational basis can be efficiently simulable, okay, for applied classical computer. But in the PDE form, like, if you want to break this up into gates, like you can't see which aspect of the PDE, okay, or which PDE, okay, requires non-Clifford gates when. Okay, and of course, just because you have non-Clifford, it doesn't mean it's not classically simulable, but at least, you know, it's a minimal condition. Okay, so, and it's also difficult to see complementarity, okay, for non-Clifford gates, like as well. Okay, but however, there's a continuous variable version of the Gottesman-Neal theorem. Okay, so Bartlett, Sanders, Bronstein, Emoto, okay, Emoto and Barry, Sanders and I, we had very, very long discussions about this. And there, in the CV case, it says only Gaussian states, gates, and measurements that can be efficiently simulable by a classical computer. Okay, so Clifford gates are like Gaussian gates, and projective measurements are like, you know, Gaussian measurements. And here, but in Schrödingerization, what I was showing you before, it's really simple to see exactly which parts of the PD requires non-Gaussianity. Okay, so, and what I mean by that is that if we look at the form of the Hamiltonian, a non-Gaussian Hamiltonian is one when it has dependence on your, you know, quadrature operators like x and p, that is more than a quadratic. Okay, and because you see, whoops, if we go back, right, and we see the form, okay, we know we can go backwards, and we know exactly whenever we have A2, if A2 is, you know, more than linear, or if A1 is more than quadratic, that's when we have non-Gaussianity, okay, and we can trace back into the origin of the original linear PD, where that comes from, okay, for example. So I mean, I haven't looked more into this yet, but this is a direction to think about, okay? Now, what I consider the benefits of Schrödingerization, okay, to be, well, first we see we can take advantage of the continuous variable simulation without considering discretization, okay, because we, you know, we've replaced the derivative, okay, with p hat. Okay, so this is really like, you know, you're you know, doing a spectral method kind of directly, all right, like looking at the Fourier component. And even in the qubit version, there's no discretization in time that is needed here. The formula is flexible and it's simple. It's not just for CV, but also for qubits. And we can actually also do hybrid, you know, CV qubit forms as well. Okay, so and then depending on, you know, which part you take to be CV, it actually maps onto different kinds of physical systems. In blue, so a lot of the approaches that people use to solve for these, they're based more or less on these matrix inversion type of methods, like HHL-based methods. Okay, but there are a lot of complications with these methods, and they depend on things like condition number or, you know, other methods like block encoding. You need to take square roots of operators, but of course you can't. So in order to approximate square roots, you need to take, you know, and not Taylor expansion, but a Chebyshev expansion of a lot of terms. So very complicated. Okay. And another benefit is that, like we were saying before, you can see explicitly which parts of the PD actually requires, you know, this minimal, you know, requirement for quantum advantage of quantum non-simulability. Okay, so including initial conditions, okay, which may be non-Gaussian, and which parts require non-Gaussian operations. Okay. And then we also may not need to break up into a lot of gates. Okay, unlike the qubit case, you have to break them up, okay, into single, you know, and 2 qubit gates. But here we can use more direct simulation, as we'll see. And lastly, our cost in terms of like spatial modes, it's in D. It's not exponential in D. As we'll see in some other examples, the gates, okay, the natural gates, that can also be less, okay, so it's not exponential, okay, in D. So even though, you know, it's, you know, can say, oh, it's, you know, you solve the curse of dimensionality, but as I was saying at the beginning, they belong in different quadrants, okay, in that 2x2, you know, table we saw. So it's really, you really shouldn't be comparing apples with oranges. Like this is really just like a new, you know, physical, you know, system to solve this equation, right? And then we should just think about it like that, okay? Because you cannot compare them directly. Like even in principle, actually, I'll just mention, so I mean, computer science is obsessed with the Turing model, right? And these are based on, you know, this bit-based method, but actually, you know, even in the classical case, analog computing is based on continuous variables, okay? And there's no Turing model for that, okay? So even basically from the, you know, computer science perspective, you cannot compare them. It's really apples and oranges, okay? So I think it's not so sensible to compare them, but if you have to, then that's the comparison to make. Okay, so now I'll talk a little bit about the applications. Okay, so some physically relevant PDEs I'll mention, and I'll also show how this method can be applied to some nonlinear PDEs and system of nonlinear ODEs. Also some PDEs which are called uncertain PDEs. So in a lot of applications, we actually are not sure about our PDE. Okay, so like the parameters of the PDE, they can be experimentally or empirically derived. So which means that they're stochastic. Okay, so how do we solve for those? Okay, and how do we put that in that setting? And then if you guys like, if we have time, then I can also mention how we can actually use this for linear algebra. Okay, so it's not exactly the PDE one. So only if we have time. So I'll just go through like some list of applications just to give you a flavor like of the form that you can see. So I'll give a very, very simple example, just, so that, you get the idea. I mean, this is, if we look at, for example, a d-dimensional convection equation, right? So this is a PDE, like very simple PDE of this form where A of j is a constant. Okay, so in this case, you see, we actually don't need Schrodingerization. Okay, so if we apply the rule, okay, that we have, derivative goes to IP hat, then already like our H, is Hermitian, right? So, and in fact, it's a sum, okay, of H of j, where each H of j has the form of, constant multiplied by P hat j. Okay, and remember P hat j, it's the momentum operator applied to the mode j. So if it's a different mode, they're independent. Okay, so which means we're summing over all the H of j's, they commute with each other. Okay, so you're really applying them independently. And in the continuous variable language, what you're doing is really displacement operation. Okay, so and it's over dq modes. Okay, so for a d-dimensional problem. Now, of course, in general, simulation of PDEs, they require entangling operations and would go beyond Gaussian operations. So this is what I would call classically simulable, right? Even though we're putting that on a quantum device, or for a photonic device, it's you're looking at the classical limit of that. But then we'll see other PDEs that actually go beyond that. We actually need these Gaussian, these entangling operations and these non-Gaussian operations. So as one example of a physical platform, so because the formalism is so simple, you can very easily go backwards. So if you have an existing favorite quantum system, okay, so for example, if we have a quantum optomechanical system that, have the natural Hamiltonian, okay, of this part, then you can see if we, do the mapping backwards, and this is done just as easily, then it naturally simulates a Schrodingerized version of this PDE here. Okay, so this PDE, it's like the Schrodinger equation, but now he has a convection term and he has a complex potential. Okay, so you can play this game as well. So in this case, it's just if you happen to be interested in this PDE, then this is one gate for you, okay, to do this. So and then if we look at, for example, linear first order, okay, PDEs, then and by first order I mean you only have like first order derivatives, okay, not high order derivatives. And then we see the ones where we only need Gaussian operations. So this is kind of the classically simulable, okay, version. Then your A is whenever your A is constant, for example, but your B, it can be linear or it can be quadratic. Okay, so we have examples of that. But then if we look at the bottom, for example, if A is linear and B is quadratic, then we actually need some non-Gaussianity. Okay. All right. So if we have even homogeneous PDE, okay, so we can deal with this by adding a qubit. I won't go too much into this because the diagram makes it look complicated, but it's really not. So it's just a lot of equations to see, but just remember, just need to add in one qubit. Okay, so now, so let's have a look at the Liouville equation. Okay, so this is like the convection equation that we saw, but except now A of j can depend on x's, for example. Okay, so now if we look at the form of H, again, it's this A2 cross eta hat plus A1 cross the identity. If we look at the form of A1 and A2, and we'll see that throughout, it has a pattern, okay, where one is the anti-commutator and one is the commutator. Okay, so and by the Poisson bracket there is just like the commutator relation, except it's a plus, okay, instead of a minus. And what is AJ? Well, we have this AJ as a function, okay, of x, but in the context of like inside the commutation relation, it's when we replace x with x hat. Okay, so as an example, if AJ is proportional to x of j, which is very common, okay, then in this case, A2 is just the identity, it's just proportional to the identity, okay, because x hat p hat, that's just I, okay. And A1, then it's actually, x hat p hat plus p hat x hat, and it's an operation which we actually call a squeezing operation. Okay, and this is very well known in quantum optics. Okay. All right, so then the Hamiltonian you need is only a displacement operation, okay, plus a squeezing operation. We have the heat equation example. This is more of a generalized heat equation example. Okay, so and again, here with A1 and A2, you kind of see that we have this, commutation and anti-commutation, okay, relation. Okay, but you can put in your favorite diffusion tensor in, okay, and you can see what you get. Now, this is something that's put in by request. Like, I know nothing whatever about finance, but people tell me they're very much interested in this equation. I cannot tell you at all what any of these symbols mean. I don't know what sigma means or r means, but all my students are very interested, okay, because they're interested in finance. So I just did this for fun, actually. So now for the Black-Scholes equation, apparently it's very important in finance. And a lot of people write quantum papers about this, but they often need a lot of resources. But here, what we do, we just need 2 Q modes here, okay, for this. And the only operation that we need, we see A1, like this is highly non-Gaussian, actually. It's not too crazy. I've been asking experimentalists about this. It's not too crazy. They can possibly do this if they try a little bit harder, okay? And then A1 here is, again, a squeezing operation that we've seen before, and that's something people can do, okay? There's a Fokker-Planck equation. Okay, so this appears everywhere, okay, in physics a lot. And actually for high dimensional ones, it also appears in finance for those of you interested. But again, I can't tell you about that, that aspect. Now, again, if you look at A1 and A2, we see there's this kind of neat anti-commutation and commutation relation, okay, between the two. I just like the mathematics of this. And again, you can put in your favorite, like diffusion, coefficient, and you also have, like, if you have drag forces and things, okay, like you can put those in as well. Okay, so it's just to show you that it's quite simple. Like, it's very simple to calculate these commutation relations by hand, and it's very different from like the qubit form where you have to take, trotterization and all of these things. But whereas like here, it's usually very simple functions of x and p, and you can really do this by hand. Okay, and even if you want to break up your Hamiltonian into different terms, you can do this by hand as well. Okay, and again, d-dimensional problem, d+1 Q modes. Yeah, again, this is a very busy slide, so I don't want you to look at anything except just to know that if you want high order time derivatives, then you add in more qubits. Okay, so for example, if you want second order time derivative, instead of 1, you add in 1 more qubit. Okay, that's it looks complicated, it's really not. Okay, it's just so an example where we need this is that at the wave equation. Okay, so the wave equation is like Schrodinger except without the I, and he has an extra derivative with respect to t. But here, as we see that we actually need this extra qubit, okay, to deal with the extra derivative, okay, in t. Okay, but then our A1 and A2, okay, it still has this, commutation versus anti-commutation relation. So then a d-dimensional wave equation, we need a d+1 Q modes plus 1 qubit. Okay, 1 extra qubit. Okay, so and this is like a summary table that we have in the paper on so some of the examples, like how many Q modes you need, and then the third column is on the maximum order term in the Hamiltonian. So this is like the most difficult gate that you need, and like the number of terms in the Hamiltonian, okay, that you need correspondingly. Okay, and I'll talk a little bit then now about the uncertain PD and the nonlinear ones. But before I go on to the nonlinear and the uncertain ones, do you guys have questions about anything?
Yeah, it's just a technical detail, but I just got a bit lost why the eta hat goes with A2. Could you just like maybe briefly explain that again?
Oh, sure. Well, actually, it's not so, I mean, I might say, oh, it's clear to see, but it's, you do have to work it out. So sorry about that if I made the impression that you're just supposed to see it immediately. But Yeah, so when I said that was more motivating why you should believe that to be true. Okay, so if we looked at the heat equation example that we went through carefully, we noticed with the heat equation, actually the form is completely anti-Hermitian, right? And we see it's anti-Hermitian because we look at the Schrodinger equation, it's minus I multiplied by Hermitian, okay, operator, but the heat equation L is just multiplied by that operator, right, Hermitian operator, which means that the full term is like the minus, if it's minus I AU, then that A is anti-Hermitian. Okay, so, right? And what we saw, okay, for that anti-Hermitian form, that we know that to Schrodingerize, we have to multiply the term by this eta. Okay, so in that blue box there. Do you see that? So,
okay.
So that's what, and then the Hamiltonian there is then, this, Laplacian plus V cross this eta hat, okay, or I put X hat here just for, as an example. Now I didn't go through the step-by-step derivation, okay, why, like H is now a sum of these, but this is just to motivate. If you take the limiting example, you see in the case that when A2 is equal to 0, then it's completely Hermitian, in which case H is just A, right? But if you take the heat equation example where A1 is 0, because A is completely anti-Hermitian, it's equal to A2 or minus A2, then that's why it's tensor product with eta hat.
Okay, yeah, thank you. That's clear. Thank you.
Okay, cool. Good question. Any other?
Any other questions? It doesn't seem to be the so yeah.
Did you have any questions, Francesco?
I'm fine, thank you. I don't know.
Oh, all right. So, okay. So now I'll talk about nonlinear PDEs. So, there have been like work where people say they solve nonlinear PDEs by through quantum algorithms, but I'm actually extremely unhappy with this. And the reason I'm very unhappy with this is that the way that it's solved is by linearizing the PDE. Okay, so when we talk about something that is linear, you can make approximations so that it's linear. And in these kinds of cases, the nonlinearity that you have to deal with is actually extremely small. And a lot of the applications where we're interested in the nonlinear behavior in the linearized limit, this is not so interesting. Okay, and I'll just very quickly go over this. I won't do every step because I realize that we're running out of time. And I'll mention, why is it difficult, right, to come up with quantum algorithms for nonlinear PDEs? Because remember, we want to map these onto Schrodinger's equation, so we can even put them on a quantum computer, which obeys Schrodinger's equation. But Schrodinger's equation is linear. Okay, so how do we actually do this mapping? And of course, like I mentioned, most of the work that has been around, and in fact, I think all of them that I've seen so far, okay, except what I'm going to talk about now, is relies on some form of linearization. Okay, but what I'll talk about today, just very briefly again, is what I call a linear representation. Okay, so transformation where you can completely transform the nonlinear PDE into a linear PDE. However, this is something that is not easy to do. You cannot do this generically for all PDEs. So we do this for the nonlinear Hamilton-Jacobi and scalar hyperbolic PDEs. So I don't know of methods for other kinds of PDEs, so this is still an open question. And in fact, when I was in Paris a couple of months ago, I was talking to the applied mathematicians there, and they told me that Schwartz, like the Cauchy-Schwartz, actually proposed this problem like a long time ago, where the mathematicians, weren't, so super interested in this, but he did propose this problem, like how do you map nonlinear PDEs into a linear PDE? Okay, and how many dimensions do you need to dilate your system to do that? And so this is still a very difficult mathematical question. Okay, but we do this, but only for these classes of PDEs. But these classes they're actually very important classes of PDEs. Okay, so yeah, but any paper that claims to do it for all PDEs, they're either using nonlinearization or I think they're not doing something right. Okay, so right, so this particular mapping, what we like to do is that if we take a d+1 dimensional nonlinear PDE with m initial conditions, then for Hamilton-Jacobi PDEs, we have a mapping that takes it to a 2D plus 1 dimensional linear PDE, okay, of Liouville form with only one initial condition, okay. And for nonlinear scalar hyperbolic PDEs, then we can turn that into a D plus 2 dimensional linear PDE with one initial condition. Okay, so and I'll just briefly talk about what this mapping actually means. Okay, so and this is just some applications of the Hamilton-Jacobi and scalar hyperbolic, and you see like it's really quite a lot of applications there. And just a note on what they are. Okay, so remember we have this general form of the nonlinear PD, and then the Hamilton-Jacobi has this form that's F. Remember, F has to be nonlinear for this to be a nonlinear PD, and the hyperbolic just has another form, like function of this F. Okay, so I realize I'm running out of time, so I'll just very quick. So don't worry about all the details of the math. I'll just describe it in words. So again, like the power of quantum is that it allows you to manipulate things in high dimensions. Okay, so what we do is that again we introduce these high dimensions. Okay, and we let quantum actually do this simulation, this high dimension, where we no longer have this cursor dimensionality. Okay, so we introduce a function we call the level set function, and it lives in a space now with one more dimension. Okay, so and how we define this level set function is that when this level set function hits 0. This is when the extra spatial parameter it actually equals to the solution that we want. Okay, and it may seem a little bit weird. It's like, okay, well that's a weird function. What's the point of that? Well, it turns out that actually this function actually obeys a linear PD. Okay, and we do some other manipulations, okay, to that as well. And this function, like itself, and we can take the initial condition as an ensemble average, okay, of the m initial conditions, and the final equation actually obeys a linear PD. And you say, well, what's the point of that? Okay, so it obeys a linear PD. Well, it turns out that actually, okay, we can do the Schrodingerization game. That's the same thing. And just some quick observations that we can do direct simulation without Schrodingerization. Okay, when Q is equal to 0. So this is when you can think about as kind of a potential term. Okay. And then the linear hyperbolic PD it only requires Gaussian operations, and the nonlinear PD that's when it requires non-Gaussian operations. Okay, that's when the quantum part comes in. And then for the nonlinear Hamilton-Jacobi, okay, it's kind of a very similar thing. We introduce this level set function. But the point of this, like you say, well, what's this weird level set kind of thing? Or it turns out that when we solve for this, we can take an inner product with a function g of p, and g of p, for example, can be 1 pp squared, and it turns out that this inner product actually corresponds to meaningful physical quantities. Okay, so like density, momentum, and kinetic energy. So what I was saying before, near the beginning about finding the right embedding. Okay, so most of it is what are called amplitude embedding. So the solution, the quantum state, has amplitudes that correspond to the solution of your PD. But now we choose kind of a weird embedding. Okay, so this level set. Okay, embedding, and it's meaningful because now we can actually find the observables, and we can find this embedding, the solution in this embedding, because it obeys a linear equation. Okay, so that's the basic method. That's the basic message there. Now, and we can also. So I won't talk about. So I'm running out of time, right, Francesco?
We might have a few minutes, and then leave a little bit of.
So okay, so I'll just state I'll just make the statements. Okay, so if we have a system for more general PDEs, of course we can we can't find this direct correspondence, but we can discretize the PDEs into a system of nonlinear ODEs. And then what we observe is that if we have a system of D nonlinear ODEs with M initial conditions, then that can actually be mapped onto a D plus 1 dimensional linear PDE, okay, with a single initial condition. Okay, and then we can do Schrodingerization there as well. I probably won't have time to talk about uncertainty quantification, but I do want to say that like in words, kind of what we do is that with uncertain PDEs, this is when the parameters of your PD, they're stochastic, they're unknown. Okay, so how people solve for this is that you have to solve for it many times, because every time you pick a sample, it's a different parameter, then you're solving for a different PD. Okay, so then if the number of samples you need is very high, okay, this can become intractable. So instead, we make a transformation, okay, so that we just need to solve for one PDE, but the observable that we have is already the ensemble average. Okay. All right. So these are two methods for that, and I won't talk about linear algebra, okay, because we're running out of time. But I just have a take-home, like some take-home messages. So this Schrodingerization method, it allows a natural mapping of any linear dimensional PD onto a continuous variable quantum system with only d+1 modes. But of course, you can also do this for, you can also use this method for qubits or hybrid things as well. But I think it's very easy to see, or more easy to see, in the continuous variable formalism. The corresponding Hamiltonian is very easy to write down, and he has potential for more direct simulation. And also the formalism allows us to see like where the real quantum resources come in. And the formalism is flexible, okay, for other types of systems. And we see that it's useful to transform PDEs into problems into slightly higher dimensions and give it a quantum treatment. Okay, so with Schrodingerization, we added this extra dimension. Nonlinear systems, we added these extra dimensions. And I didn't mention this, but for the stochastic problems, like the uncertain PDEs, we added some extra dimensions, and then they become deterministic. Okay, so these are the list of papers. So I think my collaborators, in particular, my postdoc, who actually started without knowing any quantum. Okay, so it's very good for him. So he got a faculty position recently. So in which case I'm looking for a new postdoc. Okay. All right. Thank you.
Thank you very much.
Yeah.
Just speak loud into the
Okay, thank you for your interesting talk. I just have a general question. In literature, when we talk about analog versus digital quantum computer, analog usually refers to the simulating a quantum system with another quantum system. But you didn't mention anything about the hardware, like ion traps, like neutral atoms.
Oh,
Is there
yeah.
any
Yeah. So,
cookings?
yeah. I didn't discuss particular. So we're actually talking to a lot of different experimentalists, like now, to actually compile a kind of a handbook to see how. So actually, there are ones that I didn't talk about. So there is another version of Schrodingerization. It's in the paper. I didn't mention it. Called extended Schrodingerization, and this is a form that fits more into superconducting circuits. Yeah, so for ion traps, this is more appropriate for like these hybrid type of systems, right? Because you have these ions, and then you have modes interacting with those. So what I mean by hybrids, if we go back to so if we go back to these forms, right? We can see that we can choose to discretize either the A's or the etas, for example, right? So for then for different systems, if you have a lot of ions in your system, then your A2 is better thought of as some tensor product of your Pauli matrices, okay, for example, right? So it really depends on like different physical systems. They actually require different ways of looking at this. So I only introduced the fully CV one, so in which case photonic systems like the continuous variable ones are more appropriate for this. So we actually were in contact with quite a few experimentalists like about that. Sorry, that doesn't answer your direct question, but that is something that we're working on.
And what about Xanadu, Nana? Are there any attempts to run it on a Xanadu optical computer, photonic computer? They have QMOS.
Right. Yeah. So no, I haven't been doing any simulation. So this is like just like a theoretical thing for me, because I'm more of a theorist. But I guess when I have students on board and we look at like more particular PDEs, because this is like setting up a framework. But of course, for real applications, we also need to include things like boundary conditions and all of these. We do have papers on the formalism of boundary conditions, but if you want to look at like very particular PDEs, so my students are interested in black holes, for example, then we're going to look at all these things in more detail, in which case we probably need to do simulations. But we also have some experimentalists that we're collaborating with that they want to try and do this. So yeah, so I think it's a good idea. Just I haven't done them because I'm not a big simulator person.
Okay, nice. Any other question? Anyone who wants to simulate? Any question from the online audience? Please just unmute yourself and ask.
Hi, Nana. Thank you very much for the very interesting talk.
Hi.
But have you tried to look at, when in the moment when you need to map the discrete system to the continuous variables, to things like, the atomic coherence states and things like that? In that case, in principle, in a discrete superconducting system, so in like, qubits, if you can access them on the low level, in principle, you can also have a continuous variable simulation.
Oh yeah, so this is exactly what I was saying before, that like in the paper, there's a formalism that like fits more the CV form of superconducting circuits. And this is what I call extended Schrodingerization. This is where instead of D+1 Q-modes, it's actually 2D Q-modes. So yeah, like this. So this is something I've always thought, because systems like quantum systems are naturally continuous variable, and you often have to work hard to make them dB. So it's good to look for the original Hamiltonian, like as you say, which are naturally CV. Yeah. So this is exactly. Sorry.
Okay, thank you.
Yeah. But I have to say, like, not all quantum systems like would fit into this D+1 Q-modes formalism, but then you can use the extended form, like, so you have to sacrifice a little bit, but it's not like an exponential sacrifice in terms of number of Q-modes.
Okay, thank you.
Any other questions from the online audience or from here? None. I think everybody is very happy. Thank you so much for.
So if you have any questions, I'll just put the so you can see my email. Okay. Yeah. So if you have any questions, if you think later, because you just heard it, but maybe tomorrow you're like, oh, actually, I have another question, then this is my email. And if you forget, you can ask Francesco. Yeah. And then if
Thank you.
Yeah, cool.
Thank you very much, Nana, and we will definitely receive some emails.
Okay.
And keep looking for your papers, and maybe in a little while invite you again to give us an update on other interesting developments. That would be really very nice. Please don't forget that you have an open invitation to come and visit us in Stellenbosch if you happen to be around here. Yeah, you're most welcome.
Thank you very much. Yeah. Thank you. Yeah, I would love to visit at some point.
Yeah, no, that would be great. Thank you. Thank you very much. So, Nana, have a good evening, and hope to see you again soon at some conference somewhere. Yeah.
Yeah, absolutely. Well, take care, everyone, and lovely to meet you all.
Thank you.
Okay.
Thank you. Thank you very much. Bye. Bye. Bye.